Thank you very much for the introduction. It's a great pleasure to be here. I came to McMaster, it's about 21 years ago at my very first conference before I had a university class. And I was at the University of Ottawa. They had this really cool scholarship where I was active in research. And so I came to a Quebec, Ontario Physical Organic Mini Symposium that was organized by Willie Lee at the time. So I haven't been to McMaster since, so it's a great pleasure to be here again and talk to you about what we've been doing in my research group in Kelowna, British Columbia for the past 7.5 years now. And I'm sure I don't need to go very much into the motivation of energy materials, but one thing I did want to point out is that how these United Nations Environment Programs, the UNEP, they really emphasize the fact that we're going to need net negative technologies. We're going to have to find a way in order to do some chemistry, in order to take some of the CO2 that's in the atmosphere and take it out of the atmosphere. And I think that's a real motivation for why we're looking at photocatalytic processes, because you can do some really highly active, high energy states through absorption of photons in order to drive these really uphill reactions like taking CO2 and converting it to something else. So that's the broad level. Now, just to get on the same page, when we talk about solar energy conversion systems, I'm thinking of quantum solar energy conversion, so things that are quantized, where you have a semiconductor with a valence band and conduction band that's empty of electrons until you get a photon of the right energy that can go and promote an electron into there. Now you have high energy electron, high energy hole. These are coulombically attracted to one another, so they want to come back together, annihilate and release their energy either as heat or as emission of light. And that's a waste. You absorb that photon, you want to do something else with that light energy. And so you have this electrochemical potential from the high energy electron, high energy hole. Now it took me a number of years to really realize, when you talk about electrochemical potential, you can focus on the electrical bit, and you can do electrical work with that potential difference that you get at the two terminals. And that's what photovoltaics do. It's great. But you can also take care of the chemical part of that electrochemical potential, where you have electrons that behave as reduction equivalents. You can drive reduction chemistry with that. And you've got holes that can do oxidative chemistry. You can drive oxidations with that. And that's what you want to do when you do solar fuels. So you take water, generate hydrogen fuel, and now you have something that's easily stored, transportable, et cetera. And overall, if we think about these solar energy conversion systems, the kind of big main question, okay, how can we improve the stability, the efficiency, ultimately to reduce the cost of these things? And that's a high level question. And so from my background and my expertise, this question boils down to, well, what are the charge carrier dynamics? How fast are different processes in these materials? Because that will tell us where we need to focus our efforts in order to make them better. So we can think comparison between photovoltaics and photocatalytic or photosynthetic applications when we look at kinetic timescales. So in photovoltaic, the productive process is extraction to back contacts. So you generate charges in your absorber, you go through different charge transport layers, and eventually you need to get to a contact and you need to get the charges out of your system. And that's pretty fast for photovoltaics. Nanoseconds to microseconds. Times it takes to actually reach the contact, and then at the contact, that interfacial charge transfer is very quick. If you compare that to redox reaction, the simplest redox reaction you can think of is taking a proton, shoving an electron on it. Do that twice, you get hydrogen gas. And that's, on a good day, microseconds. Really, a lot of systems operate more on millisecond timescales. So it's very slow. If you take water oxidation, you've got 2 water molecules, 4 holes. It's a really complex. There's protons going everywhere. That's milliseconds to seconds. So really, really slow compared to how fast back charges extracted at back contact are. And this is always going to be in kinetic competition with recombination. So whatever is fastest is going to win out. So you're kind of set against a wall if you're trying to do redox reactions that take seconds timescales, when recombination can be in the picosecond, nanosecond timescale. So you've got to figure out ways in order to make sure that your charges, say, reach your interface and then don't do recombination and instead do the chemistry that you want it to do. And this is a pretty easy way to say why photovoltaic panels can operate at over 20% efficiency commercially, while photocatalytic, you're maybe talking maybe 2% now on a lab scale, or maybe like 100 meter squared scale. So it's much more efficient because this is a lot faster. And we can take this kind of kinetic idea and look a bit more broadly at different types of solar energy conversion devices. We can have photovoltaics and photocatalytic, and we can also separate excitonic and non-excitonic and particulate photocatalysts, which can be a kind of mix of everything. And so here you have different band structures and different electronic landscape in how the device works. In all these cases, at some point, it absorbs light, you generate high energy charges, and it goes somewhere else. It goes on kind of two different areas. But so you have a wide range of how you can set up these systems. And what's really interesting is that you can essentially boil all of that down to this simple four-state model, where you have a ground state before you absorb light, and then you have some sort of excited state, likely between a donor and acceptor. And this can be in thermal equilibrium with the charge-separated state. And from this charge-separated state, you have some sort of forward rate constant, which actually does the function of your device. So you can extract the energy and get back your ground state of your device. So if you look at this, if you look at this energy difference here, particularly, you get that it's controlled by ratios of how much of the locally excited state you have versus the ground state, and the kinetics of the recombination here, so the deactivation pathway, and the forward functional productive process. So here already you're seeing a link between the kinetics of your systems to the thermodynamics. Because this energy difference, that's lost. If you're trying to extract the electrochemical energy from your charges, this energy is going to be dissipated as heat, and you're going to waste that energy. And so with this sort of model, well, we can take a look at what happens in real life with real devices. So we have a bunch of different types of devices. So we have both photovoltaics and photosynthetic devices on the same plot here. On the y-axis have that energy loss. So what's the energy difference between the photons you absorb and what you can actually extract out of this device? And on the x-axis, here we have the characteristic charge residence time. On the right-hand side, we have the log of the necessary lifetime gain. So this is the ratio of what's the charge residence time. So how long does a charge actually stay in the device before it's extracted, either through back contact extraction or doing redox chemistry, divided by what's the typical lifetime of that charge carrier under operating conditions. What you see is you get this really linear relationship when you look at this energy loss to the log of this kinetic ratio. And you get a slope of around 87 millielectron volt per decade. And the four-state model I showed you before was at 59.2 millielectron volt per decade. So it's pretty fascinating that you can take all these really different functioning principles and boil it down to a really simple thermodynamic four-state model, and you can get pretty darn close to what actually happens. So you're simplifying a lot of the physics there. But the really key takeaway here is that the kinetics dictate the device function. So these photosynthetic, photocatalytic, photovoltaic devices, you're not under thermal equilibrium conditions, you have the input of energy, and so kinetics is going to dictate how your device works. And that's why I care about kinetics. And so the material that we use, and I know Stuart, you gave the talk here, what, 2 weeks ago or something? And so he talked about carbon nitride. So here we have carbon nitride. So it looks like yellow brick dust. It's insoluble in anything. And you start getting this visible edge absorption in the blue, and so it looks yellow. And this really, when we talk about carbon nitride, and my group mainly talk about what's called melon carbon nitride. So you have a 1D polymer of these tricyclic fused heptazine motifs that hydrogen bond to another 1D chain to give you 2D sheets that can pi stack and give you a big particle. And so these carbon nitride materials are really easy to make. And what's really nice is that for water splitting applications, that their energy levels straddle the redox potential of water oxidation and proton reduction. So if you can put electrons in the conduction band, they have thermodynamic potential in order to reduce protons to hydrogen gas. And the holes in the valence band have the thermodynamic potential to oxidize water into oxygen and protons. So thermodynamically, this works. In practice, the efficiency at which you can convert absorbed photons into charges that do the reaction, you're talking about 5% if you're trying to oxidize water. If you're oxidizing a sacrificial electron donor, like an amine, you can go upwards of 60% or higher. So this side of the reaction works pretty darn well. But this side of the reaction doesn't work as well. And as you know, the telltale sign is that this oxidation is much more challenging, it's kinetically slow, and so the system breaks down. But if you replace this with a fast reaction, this operates pretty okay. So we want to understand, well, what's limiting these different reactions, and especially what's going on with the recombination of the charges in our photoexcited carbon nitride material. And so to do that, use transient absorption. And so it's essentially fancy time-resolved UV-Vis. UV-Vis spectroscopy, really basic method, learned in undergraduate labs, but it's really powerful when you start thinking about electronic structure, because these absorption bands are related to the excitation of electrons in your material. And so once you excite your electron, but now you've modified the electronic structure of this. So this transition where your electron was promoted is now a little harder to do because you don't have that electron that was there before to re-excite it. And so you might get a little decrease in the absorption. So that's called a ground state bleaching. And in other cases, well, now you have this electron here that wasn't there before, and you might be able to excite it even further to higher energy levels in the conduction band, for example. And that can give rise to new absorption bands that are red compared to your initial band gap. So you might get a photoinduced absorption. And what's really cool about transient absorption is that these signals, you can differentiate them spectrally. You can use things like scavengers to extract different charges, and you can get a spectral assignment. But also that these signals are proportional to the charge carrier density. That's not the case in things like time-resolved microwave spectroscopy, where the signal is the product of how many charges you have and their conductivity. And that really makes it a lot more complex. But here, if we see a signal decay over time, we know it's because of population. We can also add co-catalysts on these particles, and we could track, well, if we monitor this electron here, if the electron transfers to a co-catalyst, well, now it's no longer there, and we're going to see a decrease of that signal. So we can sometimes infer what's happening to these charges, even though we're not seeing them when they move to a different material. So this gives us access to really rich information. And this works pretty well on carbon nitride. So this is a transient absorption spectrum of carbon nitride powder. So we have here absorptance, because we're doing this in diffuse reflectance. So essentially, it's still how much does it absorb versus wavelength. And we have different spectra at 10 microseconds to 100 milliseconds. So over time, this signal decays, but you still have something at 100 milliseconds. That's really long in terms of time scales of a photoexcited state. If you take a simple molecule, usually you're going to be at 5 nanoseconds, and then it's going to be gone. But in these really disordered, messy type of organic semiconductors, inherently you get long-lived charges that go even into the second time scale. So the way that we look at this is that we have our valence band conduction band. We take here a 355 nanometer pulse, so a high energy pulse, to excite the electrons into the conduction band, but that these can trap. So these are low energy trap states that go and remove some of that electrochemical potential from your charges. So these are not good. But then what we're probing is that re-excitation from these trap states higher up into higher energy levels that could be in the conduction band, not exactly sure where they are. But we see So essentially, we can monitor these trapped charges by this vis near IR probe, and that's the signal that we're seeing there. So this signal is due to photogenerated electrons. Higher signal means you get more photogenerated electrons. So when we take a look at carbon nitride particles, this is a typical SEM that you might get. So here, 50 micron scale and a 10 micron scale. So these particles are quite big, they're chunky. This is after some manual grinding. But also you notice you get a whole bunch of different type of structures. You get some flat terraces, you got little bits and bobs sticking out everywhere. So it's a really heterogeneous looking surface. When I look at this, I'm like, well, so what happens in terms of the activity over here? What happens over here? What happens over there? And what happens to the kinetics of the photogenerated charges at these different areas? So that's what we were trying to address. So if we take a projected image of one of these particles, so we can take, not even that standard, but we can take a 250 micron spot size by taking an objective and focusing light onto our particle. Typical task measurements, you're even talking a centimeter. So you're averaging a whole bunch of different particles and getting kind of the bulk property. But here with 250 micron, well, we can take a look at one single particle. But we can't really scan it. We can't say much about what's going on in that particle. So for that, we can go even smaller to 5 microns. Now we can start scanning across this particle and see what's going on different areas of it. And so when we do typical transient absorption spectroscopy, we're really throwing away all this heterogeneity information. What's going on in different areas of your particle? So to get that information, we can do transient absorption microscopy. So here we're using a small probe size. So we're focusing the probe and we have a big excitation so that we don't have any sort of like lateral diffusion of charges across our probing area. And we do one area and we do essentially a transient absorption spectroscopy measurement there. And then we can move the stage and go to another area. And so we raster scan until we get individual kinetic spectra or kinetic decays at different spatial points in our system. And so we can build up the transient absorption microscopy image like this. So this is what the setup looks like. So we have our particle, we put it up on a glass slide. And we can use two different types of broadband light source. So that's the light that's interacting with the sample and that we're analyzing after collecting here with an off-axis parabolic mirror, because we're doing these in diffuse reflectance. So these are opaque photocatalytic particles. So we can take a broadband light source, so we can change the wavelength from a quartz tungsten halogen lamp. But this we can focus down to about 250 microns full width half max. Or we can take a laser diode, which has a much more Gaussian output of it, and we can focus it much tighter to now 5 microns, which should be even smaller if someone didn't drop the objective. So I think we should be able to get 1 or 2 micron pretty easily with a nice objective. So we can probe our particle here, shoot it with a pulse ND-YAG laser, collect the light, and we can get the transient absorption signal. So we take DCDA, dicyanide diamide, and make metal on top carbon nitride with it, and so you get a mess of little powders. And then here we literally, the tweezers, that's because this was done with tweezers, literally pick out a set of different 30 particles that we can then do individual measurements on these particles. And the measurement we do, this is what we get. So we get a transient absorption decay trace, where again we have a signal that's related to the amount of trapped electrons that we're probing. And it decays over time. So here we have 1 microsecond down to 1 second. So we get around 0.1 second here. And this decay we fit to a power law decay. This related to what we call multiple trapping and release charge transport in these sort of defect-rich semiconductor photocatalytic particles. And so we fit it, and then we take the initial amplitude, and here we take 10 microseconds. In this particular trace, we could have gone earlier, but 10 microseconds is the fastest we can really get reliable, good signal-to-noise ratio for these samples. So we get the signal amplitude. How many charges are left at 10 microseconds? And from there, we can say, well, how long does it take to decay half the charges? So we take the half-life. We take the half-life instead of the lifetime, because we're not dealing with exponential kinetics here. So the lifetime is not well defined, but the half-life, you can have any sort of shape with it, and it'll always tell you what you want to say. And so we can parameterize these sort of decays with the signal amplitude and the half-life. And so we have individual decays for a bunch of particles. And then we can fit them, get the initial amplitude, and get the half-life for all of them. And we have the microscopy, like projected microscopy image of all these different particles as well. So what does this give? So first of all, so this is two different particles. So particle 1 and particle 2. The shaded area is from a triplicate measurement on these particles to give you an idea of kind of what the experimental noise is. And they don't overlap. They're different. So the charge carrier dynamics from one particle to another are different. And these are made from the same synthetic batch, just picking two at random, but they see a difference in signal. And so we can plot this as versus the area of the particles. So we have what's the signal amplitude at T naught, which is this 10 microseconds. And we see they're all over the place. We see roughly a four-fold difference from the lowest signal amplitude to the highest signal amplitude that we get across these 30 different particles. We can do the same thing for the half-life. And here the measurement, because this is a log scale on the x, so you get some error in the fitting. And essentially, you can't really distinguish anything. And you can see the central values, too, are quite similar. So it seems that particle to particle, we can say things that there are differences in the amplitude. So there's differences in how many charges, trap charges, you have in different particles, but that their decays are pretty similar. So then we can start doing other things. So again, we have one particle here, and with our 250 micron probe beam, we take two non-overlapping spots on it, and we see the same decay. So within one particle, if you look at a 250 micron spot, it doesn't matter where you're probing. It's homogeneous on that length scale. But with that same particle, you go to a 5 micron probe, and now you start looking at two different spots, you can see these clear differences. So now you can distinguish within the same particle different areas that have different charge trapping capabilities. But you can go to a different particle at two different non-overlapping spots with, again, the small 5 micron probe beam, and now you see overlapping traces. So some particles show higher spatial heterogeneity versus others. Other particles look more homogeneous. And we can do this a little bit more refined, and we can do these maps. So here in the middle section, we have the half-life. So here, the half-life, we have a color bar scale where a short half-life, so a fast decay, is blue, and a long half-life or a long decay is red. And so here you see some red, some oranges, and here you see all blue-greens. On the right-hand side, this grayscale image is related to the signal amplitude. So this is our absorptance at 10 microsecond. A darker pixel means a lower amplitude. A lighter pixel means a higher amplitude. And so we can combine these two together to give this left-hand column, where now you can see that the top particle, you have a lot of different colors and different hues, but the bottom particle is a lot more blue-green. So it's a lot more homogeneous. It has spatially very similar composition or charge carrier dynamics at the very least over these sort of length scales. So particle 1 is a lot more heterogeneous, and particle 2 is a lot more homogeneous. And the sort of picture that we can build with this looks like this, where we know that with the big probe beam, we can see differences in signal amplitude at 250 microns if we look at two different particles. And within a particle, one of them might look more homogeneous, or more heterogeneous and more homogeneous. And that things that control the half-life from particle to particle with the 250 micron probe beam, you're not seeing those differences. But when you start probing with smaller spatial resolution, you start seeing these differences. And we can also display this like this because we don't see any correlation between the signal amplitude and the half-life. So it doesn't seem like we can say there's one type of defect that is more present at one area versus another. There seems to be two independent, at least two independent things that controls the charge carrier dynamics. But the big takeaway here is that there's particle-to-particle and spatial heterogeneities within individual particles in these carbon nitride photocatalytic particles. So now if we switch gears a little bit, so when you make carbon nitride, you choose a precursor. And the choice of precursor makes a big difference on the activity. And so here you have urea, that is the best one by roughly a factor of 2.5 here. Here urea was 10 or 20-fold better. Here, again, urea was the best one. So urea seems to be generally the best, but why? Like, for example, here, there's surface area, different things, and there's a PL intensity, and it's really hard to really see a quantitative trend there. If you compare two samples, you can say, this one has a bigger surface area compared to that one, therefore that's why it's more active. And then you look at two other samples, like, oh, the lower surface area one is more active this time. So there's really not a generalizable understanding of why would one type of melon-type carbon nitride be better than another one. Pretty consistent that urea is the best. It does show higher surface area, but not to this extent. So here it's roughly a 2-fold difference, but the activity is about 10 or 20-fold. So what's going on? So we tried to really understand that. And so we used 5 different quite typical precursors for carbon nitride. And we heated them at 550 Celsius, 4 hours at 2 degrees per minute ramp rate. So we subjected them to the same thermal conditions in order to get 5 different types of carbon nitride samples. And what we see is that we can do quantum yields for hydrogen production using a sacrificial triethanolamine solution. If we have platinum or nickel, these are the sort of the, sorry, I've got these mixed up. The top one is nickel, the bottom one is platinum. Kind of activity trends that, yeah, urea is the best. The other ones are, some difference in ordering if you do pick the nickel or platinum, but generally the trends hold pretty well. Melamine's the worst, urea's the best. These other 3 are pretty similar. And so, okay, we see differences in activity, which are very commonly reported. But again, why? Why is this? So what we did is that we took a bunch of different spectroscopic measurements. So we focused more on spectroscopy rather than material characterization. Partly that's because of our strength, and partly because people usually do material characterization and can't get an answer. And so for each sample, we looked at the FTIR, and we looked at 7 characteristic peaks in there. We took 13 bulk spectroscopic features like the band gap, the photoluminescence intensity, and we also looked at single particle features from single particle transient absorption measurements. So we have all this data set for each of our 5 samples. And so for the single particles, this is the sort of things that we get. So we have here the absorbance T naught, and we have histograms of a set of 30 different particles. And so we can take this and we can get a mean value and also a spread in order to characterize what are the results of the single particle measurements that we get. So we have all this data, and eventually we kind of boil down to these 8 key spectroscopic features. So we have a PL intensity ratio to the absorptance. This is a metric that we use to say how many reactive charges you can generate. You've got some half-lives. This is the spread, the mean. You have some absorptance, some half-life for the photoluminescence, and band gap. So we have all these different bits of information. And then we can do, okay, firstly, what's a linear correlation with the apparent quantum yield? That's ultimately what we want to be able to say something about. What influences photocatalytic activity in these materials? So at the top here is the spectroscopic features before we add platinum. In green, it's after we add platinum. And you can kind of get a quick sense from looking at them, but also from the correlation, the coefficients of correlation, that you get better predictability or more linear relations when you have the platinum. Which is not surprising. I mean, the activity is measured when you have platinum. But so going from measuring the particles or the material without the co-catalyst doesn't really link to what you see in the activity. So it's better to get the information from your material with the co-catalyst on it. Then we did this principal component analysis in order to see what is important in these samples. And what's interesting is that we can use a bunch of different type of features in them. Those are the blue lines here, the different features. And these lines give you the loadings on this, these two principal component axes. So the first two principal component axes. And regardless of how what features we use, we always see that urea stands out, semicarbazide stands out, and then these three are pretty similar. And if you look at the color of them by eye, this is what you see. Urea is a little bit whiter, semicarbazide is kind of a deep orange, and these three look yellow. So it kind of makes sense. And by activity, it's not that off. This one would be more in there than melamine, but you get this clustering. So that the high activity urea one is really distinct from the other ones. And so we can take a look at, okay, what explains urea? And ultimately, once we go down to the spectroscopic features, we really see these three features here. So we have the half-life of the bulk TAS, we have the ratio of the PL intensity to the absorptance, and we have the spread of the half-lives of the single particle. So the spread, not the mean. The mean goes towards semicarbazide, but the spread of it goes towards urea. So these seems to be the spectroscopic features that align best with activity. Those are the ones that point to the high activity urea, and in the linear correlations, it also kind of stuck out. And so with the fact that it was the spread of the half-lives when we were looking at the single particle data, led us to look at this, where we're looking at the fraction of half-lives that were greater than 360 microseconds. And this 360 microseconds is the 90th percentile of the half-lives of all the particles. So 30 particles for each of 5 samples. So the 90th percentile of those 150 half-lives is your 360 microseconds. And so melamine has no particles that has a half-life which is above that level. And urea has about 30% of its particles that have half-lives that are longer than 360 microseconds. So here we can really see that it seems like it's not exactly correlated to having a longer lifetime or half-life, but it's really what fraction tails out and has that really long. It's not necessarily what you get as the mean, but it's really those extreme values that does seem to be more related to activity. We can think of this as, well, if you have really long lifetimes or half-lives, it means that recombination in that particle is pretty slow. So now you don't have that waste pathway or that detrimental recombination pathway that is active in those urea-based carbon nitride particles. So this is when we look at different precursors using the same synthetic conditions. But there's a huge range of different synthetic parameters that you can tune. How fast do you heat it up? How long do you keep it at the high temperature? What's the high temperature? And also here we're looking where we had some methylated melamine as a co-precursor. So we're able to mix these two precursors, so the pristine melamine and the methylated melamine. What's the ratio of their mixing? How do you mix them? Do you Solubilize them together? Do you grind them together, or are they not ground? This is a huge parameter space. The synthetic parameter of this is just enormous. You could make 10,000 samples to sample things pretty accurately. And so we use a Latin hyperskew sampling in order to do a design of experiment and do sparse sampling of this really large synthetic parameter space. And we ended up with 24 carbon nitride materials. So we got 6 of them with just melamine, 6 of them with 25% methylated melamine, 50% methylated melamine, and 75% methylated melamine. So we get things like that look like this. We have a table of 24 different samples. This is how they look, and this is how they were made. So this one was all melamine. It was done at 600 Celsius, heating at 2 degrees a minute for 4 hours, etc. So we get this sparse sampling. And then we have all this, these different samples, and so let's build a data set out of this. So for each sample, we have the synthetic conditions, but then we took what's the absorptance at 20 microseconds or absorptance at T0. We have the photoluminescence intensity. We again take this ratio of the photoluminescence intensity by the absorptance. We can track different FTIR peak positions. In this case, it's the one that's related to that triazine breathing mode. Some samples show a cyano peak. It's a CN triple bond peak in the FTIR. So is it strong, very strong, or is it there or not? What's the band gap? And finally, well, what's the apparent quantum yield? So now we have this data set for 24 different type of samples. Again, let's use multivariate analysis tools in order to make sense of these. That should point out to the apparent quantum yield range goes from 0, a flat 0, and that was reproduced, just doesn't work, to 9.7%. So if we take an initial look at correlations, it's pretty messy. You can see some maybe weak correlations if you look at some of these, so the band gap, especially the PL intensity of the absorptance, or this ratio of the PL intensity with the absorptance, which kind of looks like the most linear sort of trend that we see there. But let's go a little bit deeper to this. So first we can do Pearson correlation. And so here we have 8 different features. So 4 of them are the synthetic conditions. How do we choose to make these samples? And the other 4 are, well, what's the post-synthetic properties that we measure of the sample after we've made them? And so you have the coefficient of correlation, and you also have the p-value. So if this is a big number, either positive or negative, and has a small p-value, that means it's really statistically significant, that the activity changes with that feature. And so in the synthetic features, really the methylated melamine is the most significant ones. The other ones, you really get a mixed bag, or even this is very poor statistical correlation. But if you look at the post-synthetic properties, you got the band gap energy and this PL intensity to absorptance ratio, which have really good p-values and have pretty, moderately strong correlations. And even the worst one, the PL energy, is not that bad compared to these. So here it really shows that, unfortunately, the synthetic conditions that you choose to make the material have no predictive power to how good your material is going to be. There's something that when you control these synthetic conditions, and these are what's commonly reported in terms of synthetic conditions that are controlled, it's not enough. There's something else going on in the synthesis that we aren't controlling, that we're not reporting, that is really making this kind of a nightmare in terms of reproducibility and comparison from lab to lab. But the post-synthetic properties are much better. And we also threw machine learning at this. So we have different type of machine learning algorithms. So cat boost, random forest, and XGBoost. Essentially, cat boost was the one that gave the best performance, which is nice because you can do something that's called SHAP analysis. So SHAP analysis is able to quantify how strongly does different parameters influence the quantum yield activity here. And we see this PL intensity of absorptance is by far the dominant factor that influences the activity. And second is the band gap energy. And we can notice that these two are post-synthetic properties. And we see here different synthetic properties of the percent of methylated melamine that you put in is a pretty big one for these co-precursor mixtures. But overall, the post-synthetic properties, again, dominate compared to the synthetic conditions that you're putting in. And thirdly, we can look at PCA again. And here, PCA is interesting because it's what's called an unsupervised method. We don't tell it what the apparent quantum yield is. So it can't get tricked as to why is this correlating with something. But what we can identify is that there's a high activity region where you tend to get more of the highly active samples. And the activity of the samples go from A, B, C, etc. with the letters. The numbers are those sample identification from the table I showed. And over here, so you get band gap energy, and you also get the methylated melamine. Even though it's pointing the other way, it just has a negative correlation with it. And so you see things like time and the PL intensity absorptance is in close, maybe doesn't correlate just as well, but you really see that band gap energy is the dominant factor. So in all three cases, the multivariate analyses tell us that the post-synthetic modification, the things we measure post-synthetically, the things we measure about the sample in hand are a lot more predictive and tell you a lot more about the activity than any synthetic parameters that you're dialing in when you're making it. And so we can, the takeaway here is that we can take a look at these multidimensional analyses to really look at where we need to look for quantitative relationships with activity. So 3 takeaways I hope you take with you from my talk is that kinetics really matter. Kinetics really impact device function. Secondly, that there's particle-to-particle and spatial heterogeneity within individual photocatalytic particles. And third, that these multidimensional analyses can be a really helpful tool in order to make sense of these really complex, ill-defined, amorphous photocatalytic materials. And that really we have to continue understanding these kinetically and spatially complex processes that occurs in these really not trivial materials. I'd like to thank you for your attention and thank my group for the ones that have been doing the work, especially Sutripto, who defended 2 weeks ago his PhD, and he was the lead on the transient absorption microscopy work, so he really built that up in my lab, and which is still a unique tool globally as far as I'm aware. And Peter, so this is Sutripto, and this is Peter, who led this set of 24 different samples using different methylated melamine mixtures. So thank you very much, and very happy to answer questions.
Any questions from the audience?
Really interesting work. I'm wondering, so does particle size play a role? Because I would think that as particles get smaller, they become more uniform, so you wouldn't see all that heterogeneity as much. And does using different starting materials impact the size of the particles that you produce, or is the size of the particles something that's a post-production thing of grinding the material?
Yeah, it's more of that, because once you make it, it kind of forms a cake in the bottom of the crucible. So it's a big chunk. If you could take it out properly, you might get something that's monolithic, really. But the particle size is mainly controlled by the grinding in this case. The other thing is that we were interested in the particle size effects. Let me see if I can jump to. It's not bad. It was one off. Like when we look at this sort of axes, that would be particle size, and we see no correlation whatsoever. But that's just because the length scales we're looking at here are not relevant. don't have a good number for it, but when you talk about charge diffusion length or exciton diffusion length in these materials, I suspect it's 5 nanometers kind of at most. It's really short. They're heavily trapped. And so you're going to need to go to that sort of length scales in order to see a size effect. Interesting study by Bettina Losch's group, Max Planck in Germany, is that they did ultracentrifugation to separate by size, and they saw an optimal catalytic performance at around 140 nanometers. And then afterwards it goes down. They say that the surface has catalytically relevant trap states. If you go too small, you have too many trap states. If you go too big, you don't have enough. That's kind of the indication. But yeah, looking at 140 nanometer particle size, we can't do it with this technique, unfortunately.
I've got a question about, so we've got these kind of post-synthetic properties that are good predictors for our apparent quantum yield. But then what predicts those post-synthetic properties? Look at something like band gap energy, right? I don't know, we think of it often as like a material characteristic, but evidently it is affected by the synthesis conditions because we're getting different band gap energies for different synthetic conditions. So how do we differentiate from our synthesis conditions to get those desirable post-synthetic properties?
Yeah, that's a really good question. On the band gap one, can give a bit more of an example. So urea tends to have a higher band gap. It looks a little bit wider, and it's closer to 2.9 instead of 2.7, 2.6. It's a little bit more porous. So people are saying that the sheet stacking is not as good. And so the sheets are a little bit further apart, which then shift the band gap. Because something you can, that's really interesting is that if you take the diffuse reflectance of melamine, and you take the UV vis of melamine dissolved in DMSO or ethylene glycol, there's a 40, 50 nanometer shift. So that's the electronic structure influence of having non-covalent interaction in the solid. So, and you kind of see that as well. If you put your carbon nitride powder, it looks pretty yellow. You sonicate it, it gets a little bit wider. And it's hard to really know because you make the particles smaller, then you get more scattering effects, so it's your eyes playing tricks. But I think it is really, you're reducing the amount of non-covalent interactions, and that those, I think you get some sort of, I'm not sure if they're like hexaplexes or type of different interacting bits between the pi stack things. If you make them more nanosheet-like, you push the band gap higher towards the blue. For other properties, I don't have as good of an insight as to what it is. I think really to me it comes down to when you're making these materials, the one key thing that we're not controlling is partial pressure of gases. When you do crucible, like if you take this lid versus that lid, this one's a little bit heavier, and so the partial pressure is going to be a little higher. I've been conferences and someone was like, yeah, it only works if I put 3 weights on top of the lid. If I don't put any, or if I put 1 or 2, my material sucks. So it's really to that level. And so I think this is kind of the implication, or how we think of this, is that the synthetic conditions that we control are not controlling what's actually happening in the crucible, because you don't control the partial pressure. Yeah.
Yeah, anecdotally, I've seen exactly that.
Yeah.
It's like if my lid is not tight enough, I don't get any carbon dioxide at all.
Yeah, no, it's really, it's kind of scary how much it matters. Yeah.
I was wondering, what's so special about urea that, like, maybe in terms of its properties or its structure, that made it really stand out from all the others?
Yeah. So if you look at the structure here, so when we're looking at the clustering, these 3 kind of go together, and these 2 are distinct. And the first obvious thing is like, hey, these have oxygen. And so what that means is that during the synthesis conditions, these are going to evolve water, or maybe CO2, maybe a little bit of that as well. Whereas these don't. And the way people think about carbon nitride synthesis is that you go to melamine. So that the cyanamide, for example, if you remove ammonia, you get, well, you don't even remove ammonia. You can see the cyanamide here, you see another one there, and another one there. So all of the same atoms are there. And the diamide is the same thing. But the urea, you lose stuff. So it's going to evolve more gases during that condensation polymerization step, and it's going to make it more porous. The semicarbazide hydrochloride, you also have an acid in there, and what it seems to do is that it does a bunch of defect states, because you get a tailing of absorption. So you probably get some non-fully condensed or fully formed rings, because if you protonate something, then you're not going to lose it as a gas as easily, so it might end up as a capping group. So I think really what you're doing when you change a precursor is that you're changing, again, those partial pressure of gases that you're evolving during the synthesis. Yeah.
I have like general question, more like not that specific, but I was wondering if how you see like in the future like these carbon nitride photocatalysts like working in the hydrogen production itself. Like how do you think it's supposed to be used or not?
It's a good question. I think the thing it really has going for it is just how easy and cheap it is to produce. So you can get melamine on commodity scales. It's about $300 a ton. That's cheaper than good quality dirt. Like it's literally cheaper than dirt. So that's really hard to compete with. So I have my doubts in terms of really high efficiency applications, but I think it has a fighting chance of being cheap enough that you can deploy it at much larger scales than something that works a lot better. I think in itself, the framework has, I'm not sure if it's more or less promising, but what's also nice about working on these sort of things is that it has a bunch of different applications. The carbon nitride itself, people do use it as a substrate for thermal catalysis, for example. So it has a really interesting electronic properties, so you can do a lot of different things with it, because again, it's so cheap to make. So yeah, it's hard. I mean, I would love to know and look into the future if this is going to pan out for hydrogen production. And also, I mean, I think the other relevant question is what type of carbon nitride? Is it going to be the really easy melon type, or is it going to be the harder to make but more crystalline, more well-defined, things like covalent triazine frameworks or triazine-based carbon nitrides, where you only have one ring in the middle? Yeah, not quite a exact answer, but those are my thoughts. Yeah.
Great. If there are no other questions, you can join me again in thanking Professor Godin for his presentation.
Thank you. Thank you very much.